Thank y'all everyone for joining us for another one of our BR&E 600 level webinar classes. Today we'll be talking about syngas production and more specifically steam methane reforming, and we'll look at a couple of different ways to optimize our process. My name is Samantha Moore and I will be the host for today. I am the petrochemical lead here at Bryan Research and Engineering. So if there's any questions regarding simulating any processes in the petrochemical side of the industry, I'm the point of contact there. But again, thank y'all for joining us. Let's go ahead and get started. So what we'll be covering today, we'll look at the different feedstocks for syngas production. There's a couple of different ways that we can, methods that we can take to arrive at syngas production. And then we'll look at the different applications for syngas, why it's important. And then we'll dive into steam methane reforming. We'll look at the operating parameters for that, how that might look like for some of y'all. And then lastly, we'll dive right into ProMax. We'll be, at the end of this, we'll be able to better understand how ProMax can help bring value to us in this particular area. Okay, so feedstock for syngas. What is syngas? Synthesis gas, or syngas, which is hydrogen and carbon monoxide, can be made from three main feedstocks. So the first we'll see is natural gas. So that's going to be methane. We'll take it through some steam reforming and then we'll arrive at our syngas. The other way is heavy liquid hydrocarbons, and we'll take that to partial oxidation and then sulfur removal, lastly arriving again to our syngas. And the last one, we can take coal, take that through our coal gasification, again remove that sulfur, and we will arrive at syngas. So there's a couple of different avenues that we can take. Today we're going to be looking at taking natural gas, reforming that to make our syngas, and our natural gas, that's going to be our methane. So steam methane reforming is what we're going to be focusing on. So what is syngas used for? Why is this so important? Why do we care about it? Well, there's a wide variety of different applications that syngas can be used for. As you can see from this table here, one of the big topics or the big areas that syngas is really needed in is in refineries. This is also known as a hydrogen plant. So the refineries will use the produced hydrogen for hydrotreating and hydrocracking. So that is a very big area for syngas production. We also see this a lot in ammonia facilities. The syngas production is one of the first steps in ammonia production process. The produced hydrogen and the inert nitrogen that we'll add to the system is going to help produce the ammonia downstream. And then a couple of other ways we can also use syngas to produce substitute natural gas, alkenes, methanol is another big one, aldehyde, and then we'll also see it in the production of formic acid and acetic acid. There is a lot of wide applications for syngas, but it is a very important process. Okay, so like we said, one of the steps to arrive, one of the avenues we can take to arrive at syngas from natural gas is steam methane reforming. What that is it's going to take our methane in our natural gas stream, react that with steam to produce carbon monoxide and 3 hydrogens. The picture here is a picture of our ProMax simulation. So what we're going to be looking at is the inlet steam with our methane natural gas sent through our reformer tubes. So this reaction that takes place in the reformer, it's an endothermic reaction. So therefore a high temperature is going to give us better conversion. So that's something that we're going to want to keep in the back of our mind. For this process, 1500 degrees Fahrenheit is what's going to be used for this process, and that's what we see a lot in industry. That 500 or 1500 degrees Fahrenheit is the upper limit. Like I said, we want to get that temperature as hot as possible to get the best conversion, but there is the metallurgical limit is around 1560. So we want to push it, but we don't want to go above 1560 because then we'll start to run into degradation of our material. So operating temperature, 1500 degrees Fahrenheit. Our pressure is generally going to be around 350 to 420 psig. This is going to vary from operation to operation. There's also facilities that have more than one reformer, so each reformer may have a different operating temperature and pressure. Today we're going to be using 415 psig. And the last and very important part is the steam to carbon ratio. This ratio is generally around 2.5 to 4.5. It's going to vary again based on your operation, the quality of your methane, as well as the activity of your catalyst. So is your catalyst old? Is it brand new? I mean, even the temperature. So a lot affects our ratio, but generally around 2.5 to 4.5. As you can see here in this image that we have, we're running at a ratio of 3 right in the middle. So why is this so important? So the ratio of 3, there's a lot of different reasons. The more steam that we add to the system, the better conversion we're going to get. So the less methane slip is what we'll see. Methane slip is one of the parameters that is very important to this process. We want to make sure that we minimize that slip, not only for downstream processes, but we want to convert as much of that methane as possible. So high steam is going to be better for the system. It's also going to inhibit carbon forming side reactions, aka coking. So the more steam we have, the less coking we have. If we go towards that lower bound of 2.5 or lower, we will see coke forming on our catalyst. That's not something that is ideal or what we want. So definitely something to pay attention to. And also on the ammonia side, that high amount of steam, the high steam to carbon ratio is going to be very beneficial for our downstream water gas shift reactor. So again, a lot of this is going to be really based around what particular process are you looking at. So how can ProMax bring value? Why are we looking at this today? What we're going to look at is we're going to run through a case study. So in this case study, we're going to be looking at Refinery A. Refinery A, in their SMR, they have very old catalysts. Let's think like 20 years. I don't know, very old catalyst. It's outdated. Because of COVID, they can't get their catalyst vendor to come switch it out. They're having issues and they need a meet spec. So what can we do? So that's what we're going to look at today. The catalyst isn't performing how I want it to, so I'm having issues there. Downstream equipment cannot exceed 5 mol% of methane. So the process right downstream of this primary reformer cannot take more than 5 mol% of methane. And we're currently seeing a slip of 9 mol% of methane. So we're definitely exceeding that top bound of methane slip. We need to bring that back down into normal range. And the catalyst vendor is telling me that I need to operate my steam to carbon ratio at a 6. So with that being said, let's go ahead and jump into ProMax and see how we can solve this problem. So now we're going to be looking at ProMax. It's very familiar to, should look very familiar to that PowerPoint slide we looked at earlier. As you can see here, we have our natural gas stream at 3.5 million scuffs a day, and our steam flow rate that is going to fluctuate based on the ratio that we tell it to. So what I've done here is I've set a calculator on the inlet to calculate my steam flow rate based on a ratio that I specified. Currently, our ratio is at 1.75. So it's on the low end of the spectrum. So that calculator will calculate the steam, and the steam and the natural gas will feed the primary reformer at 750 degrees Fahrenheit and 415 psig. The outlet of the reformer, again, is at 1500 degrees Fahrenheit. And as you can see here, our methane slip is 21.27. So it's pretty high, but again, we're running at a steam to carbon ratio of 1.7. So we need to clean this up. Okay, so how we're going to solve this case study, this problem that Refinery A is having. We're going to take one approach, but we're going to look at follow two different steps. The first step is we want to calibrate our ProMax reactor, this primary reformer. We want to calibrate it to match our plant data. If we just go in and set a normal reactor up in ProMax using Gibbs minimization, that's going to mimic a perfect reaction that goes to equilibrium. We know from our case study that we are not running optimally. We have a really old catalyst and that activity is really affecting our reaction. Therefore, we need a reactor that's going to mimic that loss of catalyst activity. So to do that, we're going to run through something that's called a constraint within the reactor. Before we get into that, I want to talk about what kind of reactor we're going to be using. So today we're just going to be looking at a Gibbs minimization reactor. So what is Gibbs minimization? What this is going to do is it's going to minimize the Gibbs free energy of this reactor, of the components going into the reactor. This is going to assume that this is used when the reaction goes to equilibrium or very close to it. What the benefits of using Gibbs minimization is that stoichiometry is not needed, nor is kinetic information. So it's very, very handy if you just want a quick but accurate reactor model. Gibbs minimization is a great option. The only thing, I guess, downside to this is that it's going to assume an infinite reactor length to reach equilibrium. So we're saying this reaction is going to go to equilibrium no matter what, but for the most part, it is a very, very, very handy model, and that's what we're going to be using today with the addition of our constraint. So let's talk about matching plant data. So the use of constraints in ProMax, it's really, really nice. What we've done here is we have taken operating parameters of Refinery A. So they came to us and they said, okay, Samantha, in the past 6 months, we've operated at these different ratios. So let's say in January, they had a ratio of 3 and they had a slip of 15 mole percent methane. In December, they had a ratio of 3.5 with a slip of 10 mole percent, and so on and so on. So these are 4 distinct operating parameters in the past 6 months that Refinery A has shared with us. What we've done is we've plotted them against each other. So we've taken that slip and plotted it against the ratio and found an equation for this line. This line is going to relate the slip to our ratio. So as we change the ratio, we'll be able to target a certain slip. Now, it's a very handy equation. Again, you could say, well, we can just plug in our desired slip and solve for the needed ratio. You could do that, but what if you want to look at the hydrogen produced, the duty required at that certain ratio? There's a lot that goes into it. One of the determining factors for your steam to carbon ratio and optimizing it is the duty required for the required amount of steam. So the steam production is one of the most expensive and costly parts of this operation. Therefore, minimizing your duty while also minimizing your slip is something that you constantly want to take note of. And so that's where ProMax is really going to help us. So we're going to take this equation from the plant data, and we're going to put it into our reactor in what is known as a constraint. So as you can see here, we have a blue box on our offset, which is going to dictate a calculator. We show that calculator. You can see that this equation is being put in this calculator. And from this, we can see that the mole fraction of methane out, or the methane slip, is going to be related to this equation that we found from our plant data. With that, we now have a reactor that's going to operate within those bounds in that. So it's going to be able to match our plant data a little bit more accurately and match that catalyst activity. If you have more plant data points, you can go ahead and add them as you please, and it will just make this reactor run a little bit more accurately. So once we've inputted those constraints, we can now look at the scenario tool. So that's going to be the second step in solving this case study issue that we're having. So now that we have a reactor that is performing the way we want, we can now run a scenario tool at different steam to carbon ratios and have ProMax calculate the hydrogen produced, the methane slip, and the duty required for that specific ratio. All we have to do is use the scenario tool, which is an Excel integrated tool. As you can see here, we have our different number of cases. We're going to vary that steam to carbon ratio from 3 to 5.5 with a constant gas flow rate of 3.5. So these are user-defined inputs. We decide what these values are going to be. And we're going to let ProMax calculate the rest for us. So to do that, you'll create a scenario tool. As you can see here in the top, we have our ProMax inputs, which are variables passed from Excel to ProMax. You can see we've added our steam to carbon ratio and our gas flow rate. On the bottom, we have our ProMax outputs. These are variables passed from ProMax to Excel. Here we have our hydrogen produced, our methane slip, and our duty. Once we've set this up, we can go ahead and click Run and let ProMax do the heavy lifting for us. So as you can see, I minimize this. What is happening is ProMax is taking the input variables from the Excel sheet, unsolving and resolving the ProMax file, and giving us values that we asked for. So this is a very handy tool if there's ever different variables that you would like to see displayed. Let's say maybe your natural gas flow rate is going to be varying and you want to see how low you could get, or maybe how much more natural gas you can take, and see how that's going to affect your slip or your duty requirements. Very handy tool. So just from the first couple of steps that we've taken, we can see that our C1 slip is below 5%, somewhere between case 5 and case 6. So a steam to carbon ratio somewhere between 4.6 and 4.7 is where we're likely going to want to operate. At those conditions, we're going to require about 45.5 million BTU an hour. So again, very handy tool. If there's any other information that you would like to see displayed, you simply add it to the scenario tool in our output. You would add a variable here. Let's say you wanted to look at the conversion per pass for each one of these ratios. We can throw that in there for you. this is going to be our desired operating ratio. So now that we have that, we can go back to ProMax. We're currently at a 5.5, which is too high. Let's go to our ratio and let's make this 4.5. Is that what it was? So no, 4.5 will give us 5. So let's say 4.65. So with the steam to carbon ratio of 4.65, we have 80% conversion with a slip of 4.865. So we've completely debunked the catalyst vendor telling us that we needed to run at a steam to carbon ratio of 6. Definitely saved a lot of money on duty requirement, so that is a plus. The last thing I want to show y'all before we go ahead and finish the webinar is another way we could have approached this. This graph, this scenario tool is going to show diminishing returns, which is, I guess, a way that we can see how much value we're getting out of our duty. So like I said, our steam to carbon ratio, the production of steam's very costly. So from this graph, we've taken our ratio, varied it from 1 to 5. With that corresponding ratios, we are showing the amount of methane slipped out of that primary reformer. As we increase the amount of steam, with the increasing ratios, we're also showing the amount of duty required for that amount of steam. So when we have a ratio of 4, we have a duty requirement of 20. And then we're looking at the slip to duty ratio. So what this is going to take is it's going to tell us how much conversion we're getting with the addition of 1 extra million BTU of duty. And as you can see from the graph, as we get lower and lower from our between our ratios of 3 and 5, the amount of conversion that you're getting is smaller. It's incrementally smaller and smaller as we reach 5. And if had we gone to 6, it would have really bottomed out. So for each additional of methane slip, the reduction of the methane slip, it's gonna cost us more on a duty basis. So this is another way to look at it, to really see how much money you're getting out of the steam to carbon ratio. Is how important is that methane slip to you? It's going to vary based on different processes. So again, just something else to look at and think about. But that was a quick rundown of the case study that we have. Buddy asked, what changes when the steam properties change slightly? What we've done here is we've set our pressure and let the temperature change because we know we want a light liquid going into that exchanger. If you had a higher temperature than 467, we could definitely play with that and see what happens. I suspect it shouldn't change much. And we have a question about changing the feed to this. This will work on any feedstock. So if you have a sat gas feed, H2 rich off gas from hydrotreaters, yeah, we would just go in here and change the feed to match whatever you were looking at. Johan asked, model validation, how accurate is it and what main parameters do you use to do that? So Johan, this is matching the plant data exactly. So if we ran at a ratio of, let's see, from refinery A. So they told us at a ratio of 3, they were seeing 15 mole percent methane slip. We can plug in 3 and we'll get very close to that 15 mole percent slip. You could easily match this to your reactor to see how, I guess what I'm getting at is that's how you would validate the model, is comparing it to your plant data. Oh, okay, so Simon asked about the methane slip. The methane slip is just the unreacted methane in that stream. So we simply go into the reactor effluent, we could go to our composition, but again, the analysis that was used from refinery A, everything was done on a dry basis. So there was no water in the analysis that we have from them in the case study. So what we did is we ran an analysis. In our analysis, you can choose a composition subset and remove the water and then recalculate the mole percent. So that's what we've done here. And that is how we're calculating our methane slip. All methane slip is just the unreacted methane in the reactor effluent. But thank you all again for joining us. It was a pleasure to have y'all in the webinar with me today. We look forward to working with y'all.